All the girls get down. Get up.
Hi, I'm John. I'm a chemistry graduate student at UCLA. And now in this video, we're going to be going over some chemistry topics. Hope you find this useful and good luck in your course.
Okay, so let's move on to acid dissociation constants, pKa, and relative strengths of acids and bases. So any quantitative measure of the acidity of organic acids or bases involves measuring the equilibrium concentrations of the various components in an acid-base equilibrium. The strength of an acid is then expressed by an equilibrium constant. So let's consider the familiar dissociation of acetic acid in water to form this acetate ion and hydronium ion H3O+. Now we can write an equilibrium expression for the dissociation of this or any other uncharged acid in a more general form. So dissociation of the acid, in this case we've written it as HA, in water gives an anion A- and the hydronium ion H3O+. So this equilibrium constant for this ionization here is given as KEQ. However, because water is the solvent for this reaction and its concentration changes very little when HA is added to it, we can treat the concentration of water as a constant. And then we can combine these two constants, namely our concentration of water and the KEQ, to define a new constant. And so this constant we'll call Ka, or the acid dissociation constant. Now, because dissociation constants for most acids, including organic acids, are numbers with negative exponents, acid strengths are often expressed as a pKa, where pKa is equal to the opposite log base 10 of the Ka. So I'm showing here a table that depicts the pKa values for some organic and inorganic acids. And as you go down this list, you're increasing the acidity. As you go up this list on the right-hand side, you're going from weaker conjugate bases to stronger conjugate bases. So in this table, we have the acid name, its conjugate base form, and the pKa value. So you'll probably be able to find a very similar chart in your textbooks, and so I'm going to move on and discuss a couple very important relationships. So the first relationship is that the larger the pKa value, the weaker the acid. And so then for inversely to that, we have that the smaller the pKa, the stronger the acid. Also, the weaker the acid, the stronger its conjugate base. So as you study, and again, inversely with the stronger acid, you get a weaker conjugate base. As you look at the information on the table and the similar ones in your textbooks, you'll be able to see these relationships flesh out. Now let's do a couple of example problems. So given these two chemical species, ethanol and carbonic acid, which we have given a pKa of 15.9 and 6.36 respectively, we need to calculate the corresponding value of the Ka, and we also need to determine which is the stronger acid. So recall that the pKa equals the opposite log of Ka, and therefore the Ka equals 10 to the minus the value of the pKa. So we can use this equation to calculate, therefore, the Kas of ethanol and carbonic acid. So we get 1.3 times 10 to the minus 16 and 4.4 times 10 to the minus 7, respectively. Now, because the value of the pKa for carbonic acid is smaller than that for ethanol, carbonic acid is the stronger acid, and ethanol is the weaker acid. So the next topic that we're going to discuss in the realm of acid-base reactions is the position of equilibrium. So we know from the value of the pKa for an acid whether an aqueous solution of the acid contains more molecules of undissociated acid or its ions. So a negative pKa value indicates that the majority of molecules of the acid are dissociated in water. Now, on the other hand, a positive value of the pKa indicates that most acid molecules remain undissociated in water. So HCl, for example, a strong acid, has a pKa of -7, and it's almost completely dissociated at equilibrium in aqueous solutions. Therefore, the major species that are present in equilibrium are H3O+ and Cl-. For acetic acid, on the other hand, which is a weak acid, this has a pKa of 4.76, and so the major species present at equilibrium in aqueous solutions are the acetic acid or the protonated molecules. So in those previous examples, water is the base. What if we have a base other than water as the proton acceptor? Or what if we have an acid other than a hydrogen chloride or acetic acid as the proton donor? So how do we determine quantitatively or even qualitatively which species are present at equilibrium? That is, how do we determine where the position of equilibrium lies? So if we look at this example that I have written out, of the reaction between acetic acid and ammonia, we see that there are two acids present in this chemical reaction. We have the acetic acid and the ammonium ion. There are also two bases present, ammonia and the acetate ion. So a way to analyze this equilibrium is to view it as a competition between the two bases, ammonia and the acetate ion, for a proton. The question that we have to ask then is, which of these is the stronger base? To answer that question, you need to look at the table that I had up here earlier, but you can also find in your textbooks. So you first determine which conjugate acid is the stronger acid, and couple this with the fact that the stronger the acid, the weaker its conjugate base. So we can see that the pKa of acetic acid is 4.76. You get these values from the table. And the pKa of the ammonium ion is 9.24. Therefore, the acetic acid is the stronger acid, and the ammonium ion is the weaker acid. Correspondingly, ammonia is the stronger base, and the acetate ion is the weaker base. Now, the most important concept for this is to remember that in an acid-base reaction, the position of equilibrium always favors reaction of the stronger acid and the stronger base to form the weaker acid and weaker base. Thus, at equilibrium, the major species present are the weaker acid and weaker base. Therefore, in our previous reaction between acetic acid and ammonium, the equilibrium lies to the right-hand side, and the major species present are the acetate ion and ammonium ion. Now we're going to go over how to calculate the equilibrium constants for acid-base reactions. So not only can we use the values in pKa's for each acid to estimate the position of equilibrium, but we can also use them to calculate an equilibrium constant for that reaction. So if we consider this reaction where we have an acid HA plus a base reacting to form the conjugate base A- of HA and the conjugate acid of B, or BH+. The equilibrium constant for this reaction is given here, A- multiplied by concentration of BH+ on top, and then HA and B-, HA and B on the bottom. Now, if we are to multiply the right-hand side of this equation by H3O+ over H3O+, just 1, this gives a new expression, which upon rearrangement becomes the Ka of the acid HA divided by the Ka of acid BH+. So here is that written out explicitly. So here we have that rearranged, or simplified exactly. If you were to take the logarithm of each side of this equation, we arrive at the expression of pKeq equals pKHA minus pKHB+. Therefore, if we know the pKa values of each acid in the equilibria, we can then calculate the equilibrium constant for the acid-base reaction using these steps. So you just look up the pKa values of the acid and conjugate acid involved in the reactants and the products. You subtract the pKa of the conjugate acid product from the pKa of the acid. And then because the pKeq is equal to the opposite log of KEQ, take the antilog of minus pKeq to arrive at the value of the equilibrium constant for that acid-base equation. So let's try this as an example. So we want to calculate the equilibrium constant KEQ for this acid-base reaction of phenol plus bicarbonate ion in equilibrium with the phenoxide ion and carbonic acid. So from the charts in your textbook, you can find the pKa's for these two acids. We have the phenol, this alcohol acid, and the carbonic acid. And so these pKa values are 9.95 and 6.36 respectively. And so the phenol is the weaker acid. And so because carbonic acid is stronger, position of equilibrium lies to the left. Now, to calculate the equilibrium constant KEQ, we subtract the two pKa values from one another. We have the 9.95 minus 6.36. And then we take the antilog of that value, the 3.59, to arrive at the value of the equilibrium constant KEQ.
Oh my dog, get up.